sentence-based tokenization, we can also perform word-based tokenization in NLTK. And when I talk about word-based tokenization, I'm talking about dividing a sentence into meaningful words. And just as the approaches that we followed for segmenting sentences, we can use similar approaches, but some more additional approaches to segment sentences into words. And we will be discussing few of the interfaces that are available in NLTK that can be used to efficiently segment a sentence into constituent words, namely word underscore tokenize, which is an intelligent word tokenizer which can be used, and it's a recommended tokenizer to be used in NLTK. And then we will also be exploring the regular expression tokenizer, which can also work on word-based tokenization. And then we'll be exploring the tree bank tokenizer, which uses the pen tree bank approach to tokenize sentences into words. Alright, so we will now be looking at word tokenization and how we can implement that in Python. So when it comes to word tokenization and the importance of word tokenization, word tokenization is used in many applications, and especially in text summarization, where we need to feed our machine learning model with some numerical values. But first, we need to break our sentence into individual words, and then we can form a word vector. And you can think of such applications where word tokenization would be a very useful approach, and it's usually one of the first steps to perform. And that is exactly why word tokenization is something that you really need to know if you need to build some NLP applications. All right, so in NLTK we have three of the interfaces. So the first one is word underscore tokenize, which is the default tokenizer in NLTK, and it's the most recommended one to be used. And and you will see how accurately this is able to perform tokenization on almost any language. And yes, so let's actually first import this interface from NLTK, and then I'll just go ahead and create a tokenizer variable. Okay, and once I've done that, I'll just go ahead and run this. And yes, of course, I need to actually type in a sentence here, so I'll just go ahead and type in. Okay, so when I actually go ahead and run the sentence, and what I will do now is I'll just feed this into I'll just create a, so it will, since it will be returning a list of words, so we can just go ahead and use this tokenizer here and pass in our sentence, and we will just go ahead and get the list of words and receive the list of words in this variable. And then I'll just try to print out these words. Okay, and let's see what we get. And you can see it was able to efficiently segment our sentence into individual words, and this works pretty well. But let's just do one thing. Okay, so I will just go ahead and say the quick brown fox couldn't, and you can see that this couldn't has two words, could and not. So this is a negative contraction, and let's see how this handles it. And you can see that it intelligently separates the could and not. And since we know that this nt represents the word not, and it was able to segment both of these words into two individual words. And you can kind of get the idea like how efficient this is. And we don't really need to do anything but just pass the sentence into this tokenizer. And this is quite an intelligent tokenizer because it's been trained on several languages. It's been trained on lengthy text. So all we need to do is we just need to use it, and it will pretty much perform well. So another approach that we can follow is the tree bank word tokenizer, where we use the pen tree bank approach to break the sentence into individual parts of a speech. And you might remember my first video in which I discussed the parts of speech and how a sentence is formed with different pronouns, nouns, and adjectives, and the conjunctions are joined two sentences together. And this is exactly where the pen tree bank approach comes in, where it recursively searches the sentence and breaks the sentence based on what each and every single entity represents. So for example, if we talk about this sentence, if we take a look at this sentence, you can instantly see that we have the fox represents a noun, and the jump represents an action, and so on. So you can kind of think of this whole sentence as a collection of parts of speech, and you can break this down into parts of speech. And this is exactly what tree bank word tokenizer does. So what I'll do now is I'll just try to import tree bank word tokenizer by saying from NLTK import tree bank word tokenizer, and it auto completes this for us. And now what I will do is I'll just go ahead and create an instance for this. and let's use this one. Okay, so it says, oh, we forgot to use another function that comes along with this class, which is the tokenization, which is the tokenize function that we need to use to actually call the actual tokenizer that is inside this class, right? So this is if you take a look at the documentation of TreebankWordTokenizer, you will find this function. I'll link down the documentation for this class in the description below. So if you're interested, check that out. So when I run this, it says, oh, so we need to pass in an argument which is text here. So we cannot do this. So I think I forgot to call the constructor here. So when I actually do that, let's try to run this, and you can see it works now. As you can see, this one actually gave us the similar result to the word tokenize class here, and you can see that everything looks the same. It doesn't really do anything new, but obviously if you could use a bigger corpus, you would absolutely notice some difference. So we can actually go ahead and try to load a separate corpus from the corpus collection here if you want to experiment this. But I was just actually showing this to you guys, like how you can use this essentially to perform a simple tokenization operation using this approach. And of course this one can also work well, and you can use both of these ones, but I would highly recommend you to go for this one. And you will see in our further videos, I will be creating text summarizers and text similarity checkers, where I'll be using this function very often, this word tokenization, this word tokenize function. And this is the one that is mostly used. Okay, so now we will move on to the third tokenizer instance that we have in our NLTK package, which is regular expression tokenizer. Now you might actually want to, so it might be a scenario where you want to segment a sentence into words using a particular pattern. And what we can do is we can use this regular expression tokenizer to specify a particular pattern, and then use that pattern to finally segment our sentences. So I'll just go ahead and instantly create a pattern. I'll just go ahead and create a pattern here, pattern equals, and here how you specify, you start with an R, and then you can just specify a pattern. What I'll do is I will just create a pattern for checking for just the white spaces, and that's how you do it, right? So what I'll do now is I'll actually first of all import the regular expression tokenizer from NLTK, import regular expression tokenizer, and then I'll just go ahead and create an instance of this as like this, and then I'll just call this here. I think I forgot to run this. Okay, now it's running. So I'll just call this regular expression tokenizer. And now the way how we actually go ahead and initialize this class is by first of all passing this pattern inside this tokenizer. And how we do that is we use the argument pattern, and inside this we pass in the pattern that we just created, and then I'll just pass in the gaps equals false here, and then finally we can now start using this tokenizer. So now we can just go ahead and say regex regular expression word tokenizer, and then I'll use the same. So this class also comes in with the function tokenize, just as the TreebankWordTokenizer. So you need to specify this function as well. So now what I'll do is I'll just pass in my sentence that I created above this one. The quick burn fox couldn't jump over the lazy dog. Sorry for the bad English. So now what I'll do is now I'll just go ahead and print out the words. And you can see that this one actually made a little slight mistake on the N and T. And you can kind of get the idea that this one a semicolon here, right? So this is not a semicolon, it's actually this single quote. It was not able to actually handle the single quote as I specified the single quote, and it kind of separated the N and T. This T was actually, this tokenizer actually took this T as a separate word, but that is not possible. And you can think of, as you can realize that we obviously have to improve this pattern and kind of make it adaptable to almost every single example. And that is exactly why this type of tokenizer is not recommended to be used, because it obviously requires your additional effort to create a pattern that could efficiently tokenize words And yeah, so I that is, these are the basic tokenization instances that we have in NLTK, and there are actually some other pre-trained tokenizers as well, but that is not the scope of this video. That they do not fall in the scope of this video. And most of the tokenizers that we really need to know for building our further applications are these ones. So I think you might now know what exactly these tokenizers do.